Now, every volume that we've done so far has circular cross-sections, but obviously not every solid has a circular cross-section. We can still use the same idea of summing up slices to find the volume of a shape. It's just that cross-section might not be a circle. If we can find similar shapes, then we're okay. So I'm going to start with something we know the formula for, which is a rectangular pyramid. So we should be able to come up with an answer, hopefully, that we recognise. Now, where's the number plane? Where's all these things? How on earth do we do it? Well, it doesn't really matter. All I'm going to do is say, where's my slice? I don't actually need a number plane. I could choose to slice it vertically. I would still get similar shapes. Those shapes would be, there'll be trapeziums, I think, wouldn't it, if we stop that way. Till you got to the middle, where you get a triangle, but you could sort of call that triangle a trapezium, where one side's equal to 0, I suppose. Because if you think about it, you get half base height, which is triangle. But I think an easier way is to go horizontally. Because it is a rectangular pyramid, we know every slice will be a rectangle if we go horizontally. So I've just called the thickness Z. And then I've said the dimensions of my slice are X and Y, but I somehow want to get them in terms of Z. Okay, so there's my slice. Thickness is Z. At this stage, best I've got is X times Y. So how on earth do I get Z into these measurements? So at this stage, all right, X times Y, that's no good to me. Need it in terms of Z. It's all right. Let's have a look at it. I'll just do a cross-section, and I'll do it at that triangle there. So, and I'm working out the X value first of all. So in other words, I'm saying we're looking in at X, what would we see? Well, we'd see this red triangle, which would be looking at the pyramid straight. We know the base of that triangle is B and the height of that triangle is H. And we've got a slice that's coming through it. And we know the width of that slice is X. Our question, therefore, is what's X in terms of Z? Z representing the height of the triangle at any particular point. Two ways of doing it. I could use similar triangles. So I could say, look, I've got the large triangle there, and I'm working with the right angle triangle, where the base would be half B and the height would be H. And then I've got a little triangle at the top, where the base would be half of that X value that I'm looking for, and the height would be H minus. Well, it's up to me where I define Z to be 0. I could define it at the base to be 0, and then at the top Z would be H, or I could do it the other way round. So how have I defined it? Defined the height to be H minus Z. H minus the Z value. So at the top I've got it to be 0. Because at the top, the height of the pyramid is H. So I'm saying the Z value at the top is 0. At the base, it would be there. So had I defined it the other way around, instead of H minus Z, I guess I'd have Z minus H. It doesn't really matter, as long as once I've chosen it, I'm consistent and I make sure I do it that way. So let's play around with ratio of sides and similar triangles. Don't panic, you don't have to prove they're similar or anything like that. And we end up with, there's an expression, X equals B, H minus Z over H. A lot of people like doing it that way. Personally, I prefer to actually use coordinate geometry. Again, I don't actually need to draw a number plane or anything. All I'm doing is I'm saying, well, hey, I'm trying to find a relationship between X and Z. So I'll give the slice the coordinates ZX. Now you might think, hang on, that's a bit strange. Why have you made X the second one? Because remember, I want to come up with a formula where X is the subject. And when we're creating our equations, we usually go Y equals, so what we do? So I've made it the second one, Z the first. Again, it does not matter. You could have called that point XZ if you wanted to. We're just finding a relationship between XZ. Now at the top, my coordinates then would be, well, the height is H. At the base, my coordinates are 0B. So had you have chosen your coordinate to be XZ, then obviously your points would be the other way around. You'd have 0H at the top and B0 at the bottom. My question now is, what is the relationship between the two? And there's the picture right there. As I say, I don't need the number plane. I can see the picture. I'm looking for a straight line here. So all right, I'll find the slope of that line. B minus 0, so it's always, I'm not going to say y minus y1 over x minus xy for obvious reasons, because in this one it's actually x minus x. It's always the second number on top, if you like. So we've got b minus 0 over 0 minus h. My slope is minus b on h. Put it into the point slope formula, but remembering this time it's x minus 0 is equal to minus b on h, z minus h. Make x the subject and we come up with the same equation. I personally prefer to go that way myself. Similar figures are great if it's a linear relationship. And I will concede that a lot of the problems that we get, it is a linear relationship. But sometimes it's not a linear relationship between the two variables. So I can't use similar figures for that. So, and I think I put an example in here later, we'll have a look at that. All right, but anyway, I'm not going to redo the y one because essentially the y will be exactly the same. The only difference was the base was a instead of b. But we'd have exactly the same problem to solve. So y must be a outside h minus z over h. So now we can come up with an area function in terms of z. So there it is there. Okay, tidy that up. ab h minus z squared over h squared. So there's my element of volume times delta z. And there's my sum. And I'll be going from z equals 0 to z equals h, the height of the pyramid. And if you look at actually, there's just a lot of constants there. The AB's a constant, the h squared on the bottom's a constant. We're really just integrating h minus z all squared. And we can use our useful theorem for that. Add 1 to the power over the power, but remember to multiply by the coefficient of z on the bottom. And subbing in, and we get our familiar formula of 1/3 ABH. So there it is. All right, let's try a different one. This type of one, they've actually told us the equation of the base. So it's like now our solid is sitting on the number plane, and the base of the solid is the circle x squared plus y squared is equal to 4. Now each cross section is a square perpendicular to the base. Now I always think it's good to draw pictures so you can get a feeling for what on earth is this shape. I don't know if you can think of this solid without cheating and looking there and trying to get an idea. What on earth would it look like? So right, let's lay the number plane down on the base. The circle, which when you think about it will probably look like an ellipse if we've got it lying down. So 2 minus 2, 2. Now no matter where I do my cross section, it's going to be a square. Perpendicular to the base. Well, circle's symmetric, so I could go anywhere. It makes sense to make it either parallel to the y-axis or parallel to the x-axis. So, all right, there's a square. If I went there, then the next one would go there, and so on. Starting to try and feel what this solid's going to look like, and so on. Right. It's starting to build up, and I think the closest real-world object that I can think of is a bike helmet. I don't know if that's technically true because I don't know that a bike helmet's edges go straight up. And then I'll just join those edges. Well, got a little bit dodgy there. We should get a sort of curve. I suppose essentially it's a cylinder where we've sort of shaved the top off there. It's fair to say each one of my slices I know is a square. These questions, I think, are much nicer because we actually know a relationship already because we know the equation of the base. So the thickness, the way I've drawn mine, the thickness would be delta x. So my square, well, would be twice the y value, would be the length of the square. And because it's a square, I know the height is also twice the y value. So I just need a relationship between y and x. Mind you, to make it a little bit easier for myself, I'll multiply the two together, 4y squared, because, well, we've got x squared plus y squared is 4. So I can rewrite y squared as 4 minus x squared, and we've got what we need for our problem. All right, so there's the element of the volume. We're going to sum from, now the x values, they're going from minus 2 to positive 2. Oh no, we don't need any techniques for this one. This is a fairly straightforward integral. add 1 to the power over the power, substitute in, and we have our volume of this unusual shape. Okay. Now, I think my shape or my text has moved there. It's gone over the solid. But this came from the 2012 paper, and the reason I point this one out is what I was talking about before, that it's not always going to be a linear relationship. So what we've got here is they've got a quarter of a cylinder, and they've cut like a wedge out of that quarter of a cylinder. So basically this bit in the middle here, we're trying to find the volume of. They've told us, though, if we were to slice this way, the way they've drawn their picture, we would always get a rectangle. Find the volume of the solid. So they didn't give us any hints here about saying, oh, show the areas this and all that. We've got to do everything from scratch here. So, okay, the slice they've told me is a rectangle. I'm going to call the thickness Z. So delta Z. I'll call the base X. So we're saying X is the width, if you like, there. And I'll call the height Y. I need to get some sort of relationship now between X and Y and Z. All right, again, I know the area is going to be X times Y, but that doesn't really help me right now. I want it in terms of Z. So let's have a look at Y. So again, let's just look at the shape, but I want to see Y only. So the direction that I'd have to look at it. And what I would see, that one I'd be looking straight down the cylinder. So I'd see a quarter of a circle. My slice would come down, and Y, remember we said, was the height of that slice. And now you can see what I was talking about, because you can see that relationship is circular. It's not a straight line. So I couldn't use similar shapes to find this relationship. So I'll give my slice some coordinates. I'll call them ZY. Now, I've said at the top, so I'm going to define my slicing of Z starting at A. So at A, Z will be 0, and we'll get out to the end, and Z will be whatever the radius is. So at Z equals 0, the height of the slice would be the radius, and out at the other end, when Z is the radius, the height is 0. There's the two relationships. Well, basically, it's our semicircle. Well, it's half of that semicircle. We know that relationship will just be Y equals the square root of R squared minus Z squared. I think that probably was the trickiest part of the question, because I say people are so used to just going, oh, I'll use similar figures and and it's not a straight line, so it's not going to work. All right, let's have a look at X. If I was now to look, well, I have to look down on the shape, wouldn't I? We'd see a triangle. So, because remember, so if I was to look down, I'm not going to see those curves. I'm basically going to see what looks like the base here of that triangle. That's what I'm going to see. My slice would be looking horizontal like that. Okay, well, let's give it coordinates ZX. Now, because I've already defined where Z is equal to 0, I don't change it for the other one. It's got to match up. So we said Z was 0 at the top, and at the top, my slice would also have a length of 0 as well. So that'll be 0, 0. And down the bottom, we'll have a radius and A. And we can see, yes, this is going to be a linear relationship. You can see it quite clearly there. So we are looking for the equation of a line. Slope would be A over R. And so we get X is simply just AZ over R. We can now create our function. So the area function we said was X times Y. So that's what we're going to have to end up integrating. Sum them all. Now, where are we summing from? We're going from 0 to R, aren't we? So our Z values are going from 0 to R. So our sum, there it is, 0 to R of AZ on R, square root of R squared minus Z squared. But again, we've got quite a few constants there. The A on R is a constant. That can come out the front. Oh, what do we got there? Could do a trig substitution. No, that'd be silly, wouldn't it? We just got derivative times function, haven't we? So that's probably the easiest way of doing that one. So there you go. Yep, let's put the derivative there. Minus 2z. Balance it out. Divide it by minus 2 as well. So we now know we're in the form derivative times function to the power. So add 1 to the power, 3 on 2, over the power 2/3. sub in naught, sub in R, and we're almost there. We get our volume. AR squared on 3. That certainly was a tricky one that particular year, because as I say, it was unusual. It was different to what people are not normally used to seeing. That gives you the idea. That was the average. It was 4 marks. State average was 1.01. So basically 1 out of 4. Again, because of that unusual nature of what it was. Okay. Let's have a go at these ones.